still have pink eye.
All right, well, I'll get started with a word of prayer. Let me begin here. Dear Heavenly Father, we thank you for this day. Again, I thank you for these students. I just ask that you just bless our work today. Help us to glorify you and what we do, and just to understand a little bit more about calculus 2, Lord. In your name I pray, Lord Jesus. Amen. All right, so you guys have any particular questions? Before I, yep. 101. What about it? So what in particular about 101? Okay, so example 1. Let's find the Maclaurin series. I think this 101's about, yeah, x equal to 0. It's a Maclaurin problem. Find Maclaurin series for f of x equals x cubed over 1 minus the cosine of x. All right. This problem looks different than 101, but it's actually the same. All right, essentially the same problem. All right, like what's going to happen here is going to be the same. So the way to do this is 2 steps. So number 1, you find the Maclaurin series for the denominator. And step number 2, divide. So for 101, you can also do this. All right. Now I just said find the first 3 terms, right? So I guess you have some decisions to make. Like there is another way to do this, which is just to do the 3 derivatives and evaluate at 0 for f of 0, f prime of 0, f prime of 0, which is not too much trouble. If I made it find the first 5 non-trivial terms, then it would definitely stack the deck in the favor of what I'm about to do, as opposed to the differentiation, right? I don't know, but I mean, if you guys are just beasts at differentiation, if you're just like super solid on differentiation, then the tables might turn on these analyses for me. Analyses? Seems wrong. Analyses. Okay, so 1 minus cosine of x was this. 1 minus parentheses 1 minus 1/2 x squared plus 1 over 24 x to the 4th, and then I just want the first 3 terms. So I believe that's not going to be enough. Minus 1 over 6 factorial x to the 6th. And the reason I don't believe that what I just wrote was going to be enough is what? What's about to happen? Hey. Go to your home. You see what cancels? What cancels here, right? The 1s. So 1 minus cosine x is actually equal to 1/2 x squared minus 1 over 24 x to the 4th, right? Plus 1 over 6 factorial, which is 1 over 720 x to the 6th plus dot, 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 right? All right, so I'm trying to find the Maclaurin series for this function. So what I'm going to do is I'm going to divide into x cubed this series here, right? So what do I start with? To get x cubed, I need to multiply this by, I have to multiply this term right here, right? By something to get rid of the x cubed. What do I need to put? 2x, right? So 2x And then what? And then I multiply this 2x by this and put it down here, right? So that gives me x cubed. 2 over 24 is minus 1/12. X to the 4th. Excuse me, x to the 4th? No. X to the 5th. X times x to the 4th is x to the 5th. X times x squared is x to the 7th, so I get 1 over 360 x to the 7th. And I would encourage you, so some college algebra student just sent me a question about long division, and she's like, am I right? I'm like, well, I don't know. See, because she's just kind of haphazardly denoting some of the pluses and some of the minuses, and she's doing other ones in her head. For me, I do this. I put parentheses, and I put a minus out here to remind myself I have to propagate this minus as I subtract or as I add the negation, however you want to look at it. I look at it as adding the negation. So that gives me 1/12 x to the 5th minus 1 over 360 x to the 7th. What comes next? I need to get this 1/12 as a multiple of 1/2 x to the squared. So I have to multiply this purple thing by something to get 1/12 x to the 5th, right? So what's that? I need a 1/6. What? 1/6 x cubed, right? This times that gives me 1/12 x to the 5th. And what else? Well, also 1/6 times 1/24, otherwise known as 144. So minus 144 x to the 7th. 1/144th. And, well, the next term is x to the 9th. We don't care about that, right? I'm going to ignore it. And, OK, so then I subtract. And what do I get? What's 1 over 360 minus 1 over, plus 1 over 144? I'll tell you what it is. It's time for me to get my calculator. It's time for me to realize, oh, no, phew. For a second I thought my calculator's at home. All hope is lost. I mean, well, it's not entirely true. It just takes me a minute, but, oh, man. One over 240. Let's see here. Yeah, 1 over 240. It makes sense that it's positive, right? We're adding the larger fraction. 1 over 240 x to the 7th plus stuff, right? And you don't need to know the rest of the things to know what the next term is, right? Because you just need this much to figure out the next thing here, right? Because this is the thing you're getting rid of with the next term you're adding, which is what? How do I get 1 over 240 x to the 7th? We have 1 over 120 times what? Times x to the power x to the 5th. All right. And there you go. So thus f of x is 2x plus 1/6 x cubed plus 1 over 120 x to the power 5 plus dot 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 dot. Now, I should be more careful here, because if you follow my general advice from previous lectures, what do I say next? I'm like, check your answer, right? So what happens when you go to check the answer here? How would you check your answer? What's this supposed to match up with? The more tedious way of doing this, right? F of x is f of 0. And again, you know, this might be, you know, not much more difficult. Except there's just one little wrinkle here. What's the little wrinkle? Actually, it's kind of a big wrinkle. Calculate f of 0. What do you get? 0. You get 0. I get 0 too. But you get 0 for the numerator. I get 0 for the denominator. Together we get 0 over 0, which means together we don't have meaning. I mean, this function is not defined. at 0. How do I have to define this function at 0? So technically speaking, this should be what? For x not equal to 0 and f of 0 equal to? Not 0. Oh, yes, 0. You got it. 0. Thank you. And I think it's even worse than that for this one, because I think if you calculate f prime of 0, you get what? You get, what is it? Well, you get like a, goodness gracious, I'm trying to think. It's definitely, oh yeah. So if you do the quotient rule, you still got a 1 minus cosine x squared in the denominator, right? So if you just work with this given expression, at 0, the derivatives are always of the form 0 over 0. Now, it turns out that if you study them further, they resolve to not be 0 if you like take the limit as x approaches 0. But I think I might need to well, I'm debating whether or not I also have to define f prime of 0 to be 2. I might need to do that. I don't know. I'm a little bit uncertain. I did just make up this problem, right? So, but I think the problem 101 suffers from the same fate, right? If you plug in 0, what happens? You get 0 over 0, right? Except what did I say in 101 that I've neglected to read as I was making this example up for you today? I say in 101, I said f of 0 equals 0, right? So in fact, the only way to work this problem, you can't actually do Taylor's theorem for this problem unless you're willing to take limits as x approaches 0 from the right. Like that's how you'd have to discover the values of f prime of 0 and f prime prime of 0. I'd have to differentiate and then take the limit as x approaches 0 from the right or the left or something like that to derive these values. What's easier, of course, is to find the Maclaurin series for it just directly for this kind of problem. Yeah?
So what do we do anything with the x cubed in the numerator? Or just
Oh yeah, I put it right here.
oh, okay.
Yeah.
Okay.
Now, that's a good question. Hypothetically, how would this problem change? If I traded out x cubed for sine of x, how would this go differently? What if instead of x cubed here you had sine of x? How would it go differently? All that changes is you take this x cubed right here, right? And you swap it out for x minus 1/6 x cubed plus 1 over 120 x to the 5th and so forth. You would just put the series for sine there and you could still do the problem. Yeah.
So you were saying yesterday how we can usually plug just about any value into, for instance, the pattern for cosine, the pattern for beta x, etc. Are we allowed to do nested sums? For instance, we can do x cubed times the geometric series with cosine of x as a sum, etc.
Yeah, so if you had something like cosine of x over 1 minus e to the 2x, for example. Okay, so this is the day of horrible examples, apparently. You're saying, can I go geometric on this thing, right? And yeah, I mean, you can. Sure enough, this is cosine of x times the summation n equals 0 to infinity of e to the 2x raised to the n-fold power. So in fact, yeah, this is the sum n equals 0 to infinity of cosine of x times e to the 2x 2nx. This is a series which represents that function. That is true. But the bad news is that you now have the task of developing the theory of convergence and divergence for such series in their domains, because it's not known to me, because that's not a power series. Ah, very good. So then you've got to, right, fair enough. So you're like, but that's not what I wanted to do. I was, I mean, it's all power series all the way down, right? So I was going to do 1 minus 1/2 x squared plus 1 over 24 x to the 4th plus ... That's my cosine series, right? And I'm going to multiply that by my 1 plus e to the 2x plus e to the 4x plus dot, 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 dot series, right? But then we get into the thing that I was talking about with Caleb last class, which is that while this is true, it's not terribly helpful because, annoyingly, each one of these has a 1 in it. Which makes me think that actually this is an example where maybe this calculation doesn't make sense. Because if I just look at the contribution of the constants here, I'm getting something that diverges. So I may be outside the scope of applicability. I mean, what is the scope of applicability here? This step right here, right? It's got terms and conditions, right? It needs that the radius is less than 1 in magnitude. When is e to the 2x less than 1? Well, there you've just signed on for this being true. This implies that x is an element of minus infinity to 0 not included, which is really bad news if you're looking for the Maclaurin series, because it means the Maclaurin series is outside your scope. As is being reflected by the fact that when I actually try to carry this out, I'm getting a divergent series at the level of the constant at least. So thank you for your question. I think you've inadvertently found the answer to Caleb's question last class in terms of where does this not work. Here's where it doesn't work. Like if the use of the geometric series requires the radius to be where it can't be for your application, in this case 0.
I actually divided up the E series and found that it only has this constant when, say, k equals 0, our series. And you can use that when it has a numerical value. I'm sure I did something wrong.
But 101 should be clear how to do if you use this approach, right? You peel off the constant term from subtraction of the e to the x series from 1, and then you're dividing by something. So while I don't think this is wrong, I don't think it's useful either. Okay, so like let's just erase it before I blather on more about it. Let me do another example of multiplication of series and division of series, which is a little bit more what's the word? General, perhaps. So my example 3 for today, I want to just multiply, let's see here, I want to multiply the sum n equals 0 to infinity of x to the n over n factorial times the sum, let's say j equals 0 to infinity of x to the j, oh, not x, but y to the j over n j factorial. So I'm going to use that koshy product we defined last time. How's that go here? So the koshy product says this is the sum n equals 0 to infinity of the sum. How did it go? It was k equals, there was a, was it 0 to n? No. K, k equals, oh, it was 0 to n? Oh, thank you. It was over here that I got. Okay, so then this is like my a sub n. This is like my b sub j. A sub n is one over, maybe I used a sub n bar last time, yeah? B sub bar j here is 1 over j factorial. So I was supposed to put, what was it? Was it a sub k?
Yeah.
A bar sub k, b bar sub n minus k, wasn't it?
Yeah.
And then we do, rats. So this doesn't quite fit the pattern, does it? Yeah. Yarr. Well, I'll have to fall back on more basic principles, but what I'd have here would be x to the n times y to the n minus k. That's how that would work out, all right? Forgive me, it doesn't quite fit the pattern last time, does it? I have to fall back to my original series definition and just plug in basically x sub n. What I'm trying to say is I have to fall back and I have to basically just think about putting all of this being my a sub n and all of this being my b sub j. So like that. Okay, anyway, we get to the point here. All right, so then let's put in the details. So this is the sum. Ooh, I just realized something. I think this example has to come after something I'm projecting. But let me just get to it a little bit further here. That is what? That's 1 over k factorial, right? Times 1 over n minus k factorial. X to the n, y to the n minus k. I can rewrite that as, let me just focus on just this combinatorial piece here for a second. That can be rewritten as what? That can be written as n minus k let me say this. If I trade this for n factorial times k factorial, what do I have to put upstairs in order for that to be equal to what's right above it? So I'm keeping the k factorial, okay? And I'm elevating this n minus k factorial to an n factorial. What do I have to add on to that product? I'm adding on n minus k plus 1, n minus k plus 2, n minus k plus 3, and so forth and so on, all the way on out to n, right? That's what's missing in what I wrote here. So basically, I just have to do n times n minus 1, all the way on down to n minus k plus 1. And there's another way you could write this formula. Any ideas? Oh man, I'm blanking. There's I'm forgetting something here. And I think well, there are two paths we can go down here. I think maybe I should project some things for you and we'll come back to this. Let me just tell you what happens. And there's like a little bit of a gap in my knowledge here, but this right here you can identify as the binomial coefficients. Do you guys know what the binomial coefficients are? I think some of you don't, right? Some of you do, but so here, if I do 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so forth. This is Pascal's triangle, right? And what this tells me, for example, this is 4, choose 0. This is 4, choose 1. This is 4, choose 2. This is 4, choose 3. This is 4, choose 4, if you look at it. And the binomial theorem says this. It says if you take a plus b to the n power, right, that's equal to the sum k equals 0 to n of n choose k, a to the power k, b to the power n minus k, let's say. The way that works out, generically speaking, is a to the n plus n a to the n minus 1 b plus complicated stuff plus n a b to the n minus 1 plus b to the n. So you'll notice as you look at Pascal's triangle that there's always, see these numbers? These are always n. You have n equals to 0, n equals to 1, n equals to 2, n equals to 3. The last one was n equals to 4. And that corresponds to the bookending in the binomial theorem of this n here and this n here. But this is the binomial theorem. It gives us a really efficient way of taking a plus b to the n power. This should be talked about in your algebra course, but we're afraid to tell algebra students things these days because everyone didn't learn how to add fractions, and so we're all cowering in fear because of that as instructors, right? Maybe you might not know this, but you know, things you don't learn in elementary school, they trickle up to a culture of fear and trepidation towards telling students things that they should know, which is understandable. But anyway, my point to you is after we sort things out, this is equal to actually n choose k. What I'm forgetting at the moment is the formula for n choose k, okay? The most efficient formula. But anyway, my larger point is that this right here is exactly the sum n equals 0 to infinity. Actually, it's not quite. Now I see my mistake. It's actually sum n equals 0 to 1 over n factorial x plus y to the n. So it's not n choose k. Actually, it is what? This should work out to 1 over n factorial times n choose k, actually. So this, by the binomial theorem, this doesn't go to infinity. Look at that. No, the koshy product is a series of finite sums. That's an n. So the binomial theorem is for finite, raising a plus b to a finite power, right? And so this is literally x plus y to the n divided by n factorial. And so what's that equal to? Remember, we have e to the u is what? The sum n equals 0 to infinity, 1 over n factorial, u to the power n, right? So let u equal x plus y. This is e to the x plus y. Why is that? Well, it's not surprising, is it? Because if you understand my ways, you should realize this is nothing more than e to the x times e to the y. And what you're looking at is a proof of the law of exponents using power series. Why is e to the x times e to the y e to the x plus y? This was never explained to you. Well, frankly, how did you really define e to the x in calculus? Did you? So if you had calculus 1 with Dr. Sprano, none of you did, in there he might have defined e to the x in terms of like the inverse function of the natural log. You can do this. You can define the natural log in terms of the integral. That gives a concrete definition. And then the exponential is the inverse function of that. I usually define the exponential in a kind of more circuitous way. But a good way to actually, a concrete way to define the exponential is by its power series. Like, honestly, guys, this is a perfectly good definition of the exponential. And once you have this as your definition of the exponential, then you can derive all of its properties with arguments like I have on the board. I hear from a lot of instructors of calculus too. I don't cover the binomial series. I don't think it's important. I think this is a mistake. And I think it's a mistake. So many textbooks actually de-emphasize the importance of the binomial series as well. You're like, what's the binomial series? Well, fair enough. I haven't told you yet, have I? Except at the end of last class. Let's look at it. Come on, computer. Do you guys have other questions about homework while I'm waiting for the computer to do its thing?
I was looking for the videos yesterday, and I couldn't find the videos for yesterday, the day before.
Yeah, I thought I posted yesterday. I could be wrong about that though. It may be that I forgot to post yesterday yet. I've been having some memory issues, like I'm running out of memory. So I've been like saving files on this laptop, which is a horrible thing to do. Because this is a Liberty laptop, so you never know what's going to happen, you know. For all I know, IT could like log into it and delete my stuff. I mean, I don't know why they would, but if they wanted to. Maybe I failed them in calculus years ago and I didn't know about it. I don't know. Where was I? We don't want this. Sorry guys, I'm trying to find my way to that most exciting part of class.
Didn't you badmouth IT in one of your videos? You said that IT doesn't even want to be IT or something.
I think that is a quote that may be attributable to me. Yes.
Yeah, that might be a reason.
But you know, honestly, I think if you talk to people working in IT, you'll find out that they feel the same way. There's a lot of rules. A lot of rules. There you go. Uh-oh. Well, we don't have long. Well, I suppose I've got an hour and 15 minutes. I guess that should probably do it for us, right? But whenever I see a computer, you know, battery say an hour and 50 minutes, I assume it means 15. You know, it was an hour and 15 minutes before you started doing things. It's 15 minutes after you actually start doing things, right?
One Chrome tab in the computer survives.
You should close all my Chrome tabs. Where did it go? Hopefully this is it.
697, I think, or something.
Yeah, six.
Oh, I actually got it. Yo, let's go. I have my brain actually. It's so important. Top hat did not support the fedora.
Top hat is important, but not as important as the fedora. I like that. I'll allow it. Oh, top hat twice.
2 top hats. Yeah.
Top hat 2 times, yes. Thank you for reminding me, because we forgot the top hat yesterday, so. There you go. Do you want to just get it out of the way for tomorrow?
Yeah.
All right.
I didn't get either.
Well, I'll leave this one up for you,
It's all good.
Austin. All right, where was I?
Plan on being here tomorrow.
Oh, you plan on being here? Okay, so let me get to it here. Sorry, the computer will eventually bend to my ways. Here we go. Oh, I forgot why. I'm now remembering why I don't use this projector. It's like somehow it's always shaking up and down. Yes, sir.
This might not work similar to the Taylor series, but on that example one that we did for the homework, could you use that McLaren series for the alternative error?
What are we talking about? I'm sorry.
Example where you did x with the negative 1 minus cosine x, use the McLaren series for that by taking 1 minus cosine x to the negative 1. That might sound confusing. On the board.
Do you mean use? You're saying take cosine.
Negative cosine x is rooted, and then delta would be -1. Or whatever it is.
Alpha.
Yeah, alpha is right.
Yeah, that's a possibility, right? Yeah. But that's not insane, because the reason that the reason that it's a tractable calculation is because when we take 1 minus cosine, the lowest order term in it is x squared. So as you're thinking about these things like alpha x and so forth and so on, at least you don't have that issue of all the constants. But there's something amiss though. Oh, I think I know what you're saying. I think I know what you're saying. I was about to attribute something that you weren't meaning. So let me try this. So what you were saying is take x cubed, leave it out here by its lonesome, and look at this as 1 minus cosine x to the minus 1 power, and use the binomial formula with alpha equals to 1 to do it. I think you could do that. But you'd have to be careful about making sure you're not missing terms, because like x squared, so the thing that you're calling x, oh goodness gracious, have I erased it? No, I still have it. So that is 1/2 x squared minus 1/24 x to the 4th. I'll just do that much, okay? Oh yeah, no, so again, you're saying let u equal cosine. No, I don't want to do that, because u will have the 1 in it when I expand it as the cosine, as the Maclaurin series. So every power, see, since your u is, if you let u equals, the x here becomes the u. If you let that be cosine, then x to the 10th still has a constant term in it, because cosine is 1 minus 1/2 x squared, and as you like raise that to the 10th power, you still got, it's in contrast, if this was the thing I was powering, then that would be okay, because there's no constant term, and like each term, if I take this and I square it, right, then the lowest order term in that is order 4. And so if you don't have a constant term in the thing you're squaring, it's more amenable to the trick you're talking about. It's a good question, but it's the same hard question you guys keep asking. So, all right, so let's just talk about this here. This is the, so what I'm doing, like, slow down for a second here, take a breath. It's very simple. I'm looking at the function f of x is equal to 1 plus x to a power. All right? So unlike the binomial theorem I just had up on the board behind this, I'm not assuming the power is an integer. It could be a half, it could be -1, it could be a third, alpha could be pi. I mean, whatever. It's just a power, all right? A real number. And when I differentiate this function, it's pretty easy to differentiate, right? Differentiate once, I get alpha, 1 plus x to the alpha minus 1. My apologies again for the shaking here. I can't. Why does that shake so much? Anyway, there must be somebody with like an office like right there, and they're just sitting there like they were their foot, you know? Some of you guys try to take notes in a class with somebody doing that next to you, don't you? You've experienced it. You know what I'm talking about. Alpha times alpha minus 1, 1 plus x to the alpha minus 2, and you see the story goes on, right? After we differentiate n-fold times, we get a bunch of these all the way down to alpha minus n minus 1, all right? And then I evaluated 0 to figure out the coefficients for the Maclaurin series, right? It looks like that. And I put it together. So 1 plus x to the alpha is alpha times alpha minus 1, dot, 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 alpha minus n minus 1, all divided by n factorial x to the n. And so the pattern is just this: 1 plus alpha x plus alpha times alpha minus 1 over 2x squared plus alpha times alpha minus 1 times alpha minus 2 over 3 factorial x cubed, and so the story goes. All right? And so this result is known as the binomial series. I think this is an important example to know about. I'm actually more interested that you know this formulation. Like, it's important to know these first 3 terms. I guess that's 4 terms. The first 4 terms, it's actually more important that you know these first 4 terms than you know this. Because more often than not, when I ask you to use the binomial series, I'm asking you to use it as part of a problem to find the first 3 non-trivial terms. Like that happens in your homework. Basically, this is the tool you need to solve problem 99. Yeah. Thank you. Okay, so let me show you an example here. Well, yep.
What if x is greater than the power of 1?
What if x is greater than the power of 1? What do you mean?
Like, so for this example, you have x plus 1 plus x to the power of alpha.
Yeah.
And the one below is 1 plus x to the power of 4. Like, what if it's like 1 plus x squared to the power of 4?
You would set x greater than.
Yeah, I can replace x with u here,
And it just doesn't change.
and I can just substitute in u, and you can make a substitution here. Yeah. Yeah. I mean, it will change the applicability of it. I think when you study this, how would you figure out the interval of convergence for this thing? Ratio test, right? And when you do that, it turns out, I think, that it's like -1 to 1. This converges -1 to 1. And then it's a complicated story. I don't remember. It depends on the choice of alpha. You may or may not include endpoints. So that's, I don't remember that. I'd have to look it up. But, oops. Come on. I mean, of course, this overlaps, right? This is the geometric series when alpha equals to -1, right? When alpha equals to -1, what happens here? You had 1 over 1 plus x, right? And you already know what that goes. You already know what happens there, right? 1 plus x to the -1 is 1 over 1 plus x, right? Which is the summation n equals 0 to infinity minus 1 to the n, x to the n. So that there's a place where the binomial series overlaps with the geometric series. So sometimes you can bring more than one tool to bear on a problem, like this one, that one there. But the other thing I think it's worth everyone to know about, certainly for math majors, but also for engineers, because you guys would like to know about high school algebra, right? And what I'm talking about is high school algebra, binomial theorem. So here's 1 plus x to the 4th. It's this, and here's the formulas for it. 4 times 3 over 2, 4 times 3 times 2 over 3 factorial. Like, these numbers are those numbers. And so this is the n choose k. N choose k, here's the formula I couldn't remember. N times n minus 1, n minus k minus 1 over k factorial, which is exactly this. I think that's what we had. Yeah, little n is big N, but yeah, maybe. Yeah. So if you change this little big N to a little n, that's the formula we had, because there's like a 1 over n. Anyway, let me shut up. So here's the 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. But the numbers for the choose you can get from the Pascal's triangle if you want. And listen, for the record, everything I'm telling you right now, I will not test you on. This should fall under the auspices of like a probability and statistics class that you guys will take, right? So let's leave it to be tested there. I don't test on counting. I can't count. It's been well established. For that reason, I've included an example. If you have toys, A, B, C, D, and you want to pick 2 of them, there are 6 possible selections. See, because 4 choose 2 is 6, corresponding to either AB, AC, AD, BC, BD, or CD. These are the 6 distinct ways to give 2 toys from a selection of 4. So that's the combinatorial meaning of this n choose k. All right, you may or may not have seen this before. Or if you want to choose, you got 10 toppings to put on a pizza, and you want to choose 4 distinct toppings. All right, there are 210 possible such pizzas. Now, if you're actually going into the pizza business, this isn't the calculation for you, because of course you might find somebody who wants what? Cheese times 4. That's not accounted for in these countings, right? Or no toppings. If you want to count like all possible toppings where you could have repeats, I think it's just 10 to the 4th. I think it's what, 10,000? Yeah. Anyway, let me stop talking about counting. No one cares. So here is an example for you guys. If you're in my physics class, you've seen this already. but maybe not explained. So gamma is this 1 over the square root of 1 minus v squared over c squared. And I can find a series expansion for this using the binomial series with alpha equals to minus 1/2. I've got 1 plus alpha, which in this case is minus 1/2 u, and then plus 1/2 of alpha times alpha minus 1, which gives me a minus 1/2 and minus 3/2. And then I've got the product of minus 1/2, minus 3/2, minus 5/2. I kept the minus out here. And that works out to this 1 minus 1/2 u plus 3/8 u squared minus 5/16 u cubed. So the power series expansion for this gamma function, expanding it in u equals v squared over c squared, is just this. And when you multiply that, you get mc squared plus 1/2 mv squared plus 3/8 mv to the 4th over c squared plus these terms. Now, so this is Einstein's E equals mc squared formula that you've probably heard about somewhere. And if you take physics, you learn that this is the classical kinetic energy. And then these terms are really, really small if v is close to, if v is much smaller than c, then these are very, very negligible. So, but the rest energy, mc squared, is actually much bigger than the classical kinetic energy, which is, why you can't ignore this if you want to understand nature. So, but anyway, I think that's an interesting example. Another interesting example, possibly from physics. I mean, definitely from physics. The question is whether or not it's interesting. I think it's interesting. The acceleration due to gravity at altitude h is given by minus gm over r plus h quantity squared. This comes from Newton's universal law of gravitation and Newton's second law. If I expand this, so whenever you're doing an application of a power series, you want to expand in something that's small, right? So if you think about altitude with respect to, say, radius of the Earth, which is bigger, the altitude or the radius of the Earth? Well, in our everyday experience, right, unless we're up on the space, what's it called, the space station, or unless you go live on the moon or something, right? What?
The ISS.
Oh, the ISS? That's awful close to ISIS, isn't it? Yeah. That must have been labeled before that, right? But anyway, I'm sorry. Do I need to be more nuanced in my treatment of ISIS? Like, are they the good guys now? I mean, what happened? I don't know. I don't watch the news, so whatever. Are they all dead? Yeah. Well, that's good. So, you say America. I'll allow it. Let's see here. So, if I want to rewrite this in terms of h over r, so to do that, I factor out r squared. And that gives me this, at which point I've got gm over r squared times 1 plus h over r to the minus 2 power. I can expand this as a series with alpha equals to minus 2. Only the first two terms, the 1 plus alpha u, that's all that matters to us here. So 1 plus alpha, because alpha is minus 2, h over r. And so what you get is that the acceleration due to gravity is about 9.83 meters per second squared plus or minus 2 gm over h, 2 gm h over r cubed, where 2 gm over r cubed is about 3.1 times 10 to the minus 6 over second squared. So to make it more specific, if you make your altitude, let's say you make your altitude 1,000,000 meters. That's pretty big, right? 1,000,000 meters, like 1,000 kilometers. That's like what? 1,600 kilometers is 1,000 miles, right? So it's a little shy of 1,000 miles, maybe 700 miles or whatever. So 700 miles up, your acceleration due to gravity drops by 3 meters per second squared. So if you go about 700 miles up, straight up, your gravitation is dropped from 9.8 to about 6.8. Possibly. I mean, that's what the error bounds say here anyway. I'm not saying it's exactly that, but so you can see that saying acceleration due to gravity is 9.83 meters per second squared is pretty stable as long as your h is relatively small. But if you go too far up, you could start to maybe measure a decline in the acceleration due to gravity. In fact, the more significant effect on the surface of the Earth is not altitude, it's what? Yeah. Oh. The more significant effect on the surface of the Earth is the centripetal acceleration, right? So like on the equator, you have a larger centripetal acceleration because you're spinning further around the axis around which the Earth spins. So, are you guys flat Earth?
Donut Earth, actually.
What's that? Donut Earth? I believe in the cylindrical Earth. But see, I say that the ice walls at the caps, they're not actually walls. They're actually entrances to the interior Earth. So, although the one on the North Pole is covered by water, so you can only access it by submarine. But once you go through the portal inside, you're inside the interior ocean. That's where the no, the Amish. Actually, it's a collection. It's a society of lost, technologically advanced Amish. They practice something called woodtronics. You can only, like woodtronics, you connect the circuits with the the heartwood of an oak, 1,000-year-old oak. It can only be harvested in the moonlight. So, what's that? Things like this. Yes. What?
Journey to the cylinder of the Earth.
Journey to the cylinder of the Earth. Yeah.
So, what is the discrepancy in the acceleration of the Earth?
Oh, I think that's just the numbers I ran, but we usually use 9.8. So I think it's just, we don't want to use 9.83, so we use 9.8. I've seen 9.82 used in some other books. It varies. 9.81, yeah.
9.81, 9.80.
When I ran the numbers on the mass of the Earth and the radius of the Earth I looked up, that's what I got. So, it could be a miscalculation on my part for all I know. All right, so if you're wondering why I have so much to say about the flat Earth and why I have prepared a story about the cylindrical Earth, the reason is that I joined a Facebook group on the flat Earth, and I decided to work on my theory of the cylindrical Earth for some time. So I've created some lore for it. I'm still working on it. It's not complete yet. I will admit, I did once vote for a flat Earth candidate, but I felt like him being the governor of Alabama, it was relatively, NASA probably would be relatively safe from him. Whatever he thought of NASA, I thought, he's the governor of Alabama, it'll be okay. So, he lost a lot. But listen, so I do owe you guys a discussion about the proof of Taylor's theorem. So let's do that now, since I have this out, and you're already a little bit motion sick from the bouncing. So when I teach Calculus 1, I actually teach Taylor's theorem in Calculus 1. And the reason for that is pretty simple. It's that Taylor's theorem about polynomials is a natural extension of the mean value theorem. So do you guys remember what the mean value theorem said? If I put the mean value theorem on the quiz tomorrow, would that be a good thing? No, that would be a very bad thing. But the mean value theorem says this. It says that there exists C, an element of AB, such that f prime of C is equal to f of B minus f of A over B minus A. Now there are terms and conditions here, right? Assuming that the function is continuous on the interval a to b and differentiable on the interval a to b. I think it has to be continuous on the closed interval. It has to be differentiable on the open interval. If all of that's true, then you get f prime. There exists a C such that f prime of C is equal to f of b minus f of a is equal to f prime of C. Now what does that say in plain language? In plain language, the mean value theorem simply says that if for a function sufficiently nice, there's a place inside any open interval such that the average rate of change over that open interval is equal to the instantaneous rate of change at some point in that interval. See, if you think of the x as being time and f of x as being position, this becomes velocity is equal to the average velocity. This is what this becomes. This is what the mean value theorem says. It turns out that there's a mean value theorem for polynomial, like you can generalize this. And what this theorem says essentially is that if I take a function, all right, I can approximate that function by the Taylor polynomial to order n, all right? And, oh, fine, I guess I should say this. Another way to look at this is f of b is equal to f of a plus f prime of c times b minus a. So what you're looking at is the linearization of f at a evaluated at b. So the mean value theorem is really saying that it's making a comment about how well the linearization does as an approximation for the function. Taylor's theorem makes a comment about how well Taylor's polynomial centered at a does as an approximation for the function as it relates to the value of the function at b. So I know this is, I don't expect you to memorize this or anything like that, but I just wanted to let you know you can write this down. Now here, this is the remainder term. That's capturing the error in the Taylor polynomial to order k, centered at a. And more than that, you get that this error term you can write in terms of the next derivative you haven't used, get the k plus 1th derivative of a k plus 1 factorial times this. The proof of this is actually pretty much the same as the proof of the mean value theorem. I mean, here it is. Basically, you just write down, I define a constant m by this equation. I write down a formula that amounts to this is 0, being that the Taylor's theorem is working. You end up applying Rolle's theorem, and you do some calculations, which we don't need to go through really, because you guys have asked me interesting questions about things, and it's used up our time, which is probably better use of our time anyway. But here is the proof. It's all here. And when you sort through it, again, like the proof of it ultimately rests on Rolle's theorem, which is also how you prove the mean value theorem. And in Rolle's mean value theorem, you look at the secant line, and you take like the difference of the secant line and a point, and then you apply Rolle's theorem to that function, and then that gives you the mean value theorem. In the same way, we look at the difference between the function and the kth Taylor polynomial, apply Rolle's theorem to that, and that's how we get Taylor's theorem. So the thing that I think I may have assigned you some homework from Stuart that you probably haven't looked at yet at the end of this mission that might involve this, maybe. So we'll talk more about, I'll do some specific examples with this maybe next week probably. This gives us an error bound. So if you, so like it says, if a function has k plus 1 continuous derivatives on a closed interval p to q, and the length of that interval is L, then if you can bound the k plus 1th derivative by m, then the error in the Taylor polynomial of order k is at most, the size of it, m times the length of the interval to the k plus 1 power divided by k plus 1 factorial. So you see what this does? You see what happens here? Think about what happens as k goes to infinity. See, as k goes to infinity in this, then you're looking at the Taylor series, right? So what does it take for the function to be equal to its Taylor series as k goes to infinity? What has to happen? This other term here, this remainder term, what has to happen? It has to die, right? So a way of defining analyticity of a function, in other words, that the function matches its Taylor series, is to say that the limit of the remainder goes to 0. So to prove that the function is analytic, in other words, that it matches its Taylor series, you have to give evidence that the remainder term gets small. We have not done that for anything.
Where does m come from?
M is a bound. Let's look at an example. So suppose you want to put this into practice. Let's prove that sine. Let's prove that sine actually is analytic on the reals. All right. So sine is what? What example am I on? 4. Okay. Cool. So f of x equals to sine x, right? So I think we did this before. What is the well, f prime of x, I'll just do it again here. F prime of x is cosine x, yeah? F prime prime is minus sine x, right? Let's see here, the odd derivative is minus 1 to the k sine x, right? The